C is really a very simple language, so it should be no problem to do this, right? So C is two things, actually. It's really important. I think you were just talking about why it's actually very useful. There's tons of code available in C. A lot of that C is really useful. But C is actually a terrible, crazy, gross language on its own right. C has all these horrible things in it, like pointers that are horribly unsafe.
And we have a question.
Oh, let's do it.
Is it possible to achieve similar results in Python using something like Python?
Yeah, absolutely. So Python is a Python-like language which compiles to C. And I would generally rather write Python than C for integrating C with Python. You still kind of, it's actually easier in a Jupyter notebook because you can just say %% Python and kind of integrate it. But as soon as you want to start shipping a module with that thing, which presumably is the purpose is you want to share it, you then have to deal with like build scripts and stuff like that. So like Python has done an amazing job of kind of making it as easy as possible. But I personally have tried to do quite a lot with Python in the last few months and ended up swearing off it because it's just still not convenient enough. I can't quite use a normal debugger and a normal profiler and just ship the code directly, and it's still, yeah, it's great for Python if that's what you're working with, but it's nowhere near as convenient for, like, I've created SwiftC libraries. I created a SwiftC library within a week of starting to use Swift. It was just very natural.
Cool. And so the thing I want to underscore here is that C is actually really complicated. C has macros. It's got this preprocessor thing going on. It's got bit fields and unions and this weird notion of what vargs are. It's got volatile. It's got all this crazy stuff. That the grammar is context sensitive and gross. And so it's just actually really hard to deal with.
You sound like somebody who's been through the process of writing a C compiler and came out the other side.
Well, so the only thing worse than C is C++. And it has this like dual side of it. It's both more gross and huge, and it's also more important in some ways. And so Swift doesn't integrate with C++ today, but we want to be able to. We want to be able to provide the same level of integration that you just saw with C and C++. But how are we going to do that? Well, Swift loves C APIs, like Jeremy was just saying. And so we love C APIs because we want you to be able to directly access all this cool functionality that exists in the world. And so the way it works, as you just saw, is we take the C ideas and remap them into Swift. And so because of that, because they're native, pure Swift things, that's where you get the debugger integration. That's where you get code completion. That's where you get all the things you expect to work in Swift, talking to Dusty Deck, old grody C code from the 80s or wherever you got it from, whatever epoch. And we also don't want to have wrappers or overhead because that's totally not what Swift's about. So Jeremy showed you that usually when you import the C API into Swift, it looks like a C API. And so you could, but the nice thing about that is that you can build the APIs that you want to wrap it, and you can build your abstractions and make that all good in Swift. So one of the ways this happens is that inside the Swift compiler, it can actually read C header files. And so we don't have a great way to plug this into workbooks quite yet, but Swift can actually take a C header file, like math.h, which has macros. Here's m_e, because m_e is a good way to name e, apparently. Here's the old school square root. Here's the sine cos function, which, you know, of course, it returns sine and cosine through pointers because C doesn't have tuples, right? And so when you import all that stuff into into Swift, you get m_e as a double that you can get. You have square root, and you can totally call square root. You have sine cos. You get this unsafe mutable pointer double thing, which we'll talk about later. Similarly, like malloc, free, realloc, all this stuff exists. And so just to show you how crazy this is, let's see if we can do the side-by-side thing. Can you make it do side-by-side?
Is that a challenge?
Yes. My Windows skills are dusty. Check it out. Okay, beautiful. So what we have here is we have the original header file, math.h, on the left. And if you look at this, you'll see lots of horrible things in C that everybody forgets about because you never write C like this. But this is what C looks like when you're talking about libraries. So we've got a whole bunch of if-defs, we've got macros, we've got like crazy macros. We've got conditionally enabled things. We've got, these things are also macros. We've got inline functions. We've got tons and tons and tons of stuff. We've got comments. We've got structures, like exception, of course. That's an exception, right? So when you import this into Swift, this is what the Swift compiler sees. You see something that looks very similar, but this is all Swift syntax. So you see you get the header, the comments, you get all the same functions, you get all of the, like here's your m_e, and you get your structures as well, and this all comes right in, and this is why Swift can see it. Now, how does this work? That's the big magic question. So if you want to get this to work, what you can do is you can build into the Swift compiler, we can write a C parser, right? And we can implement a C preprocessor, and we can implement all the weird rules in C. Someday we can extend it and write C++ as well, and we can build as this library, so the Swift compiler knows how to parse C code. And a C++ compiler is pretty easy to write, so we can hack that out in a weekend. Or, yay, good news, like we've already done this many years ago, it's called Clang. So what Clang is it's a C++ compiler. Oh, this is getting even, just to even more talk about how horrible C is, you actually get, you get inline functions. Inline functions, the insane thing about inline functions is that they don't exist anywhere in a program unless you use them, right? They get inlined. And so if you want to be able to call this function from C, you actually have to code gen, you have to be able to parse that, code gen, understand what unions are now, understand all of this crazy stuff just so you can get the sign bit out of a float, right? C also has things like function pointers and macros and tons of other stuff that's just, it's just madness. And so the right way to do this is to build a C compiler. And the C compiler we have is called Clang. And so what ends up happening is that when Jeremy says import socks, Swift goes and says, haha, what's a socks? Oh, it's a module. Okay, what is a module? Oh, it's C. Oh, it's got a header file. Fire up Clang. Go parse that header file. Go parse all the things the header file pulls in. That's what an umbrella header is. And go pull the entire universe of C together into that module, and then build what's called syntax trees to represent all the C stuff. Well, now we've got a very perfect, pristine C view of the world, the exact same way a C compiler does. And so what we can do then is we can build this integration between Clang and between Swift, where when you say, give me malloc, or give me socks in it, Swift says, whoa, what is that? Hey, Clang, do you know what this is? And Clang says, oh yeah, I know what socks in it is. It's this weird function. It takes all these pointers and blah, blah, blah. And Swift says, okay, cool. I will remap your pointers into my unsafe pointer. I will remap your int into my int32, because the languages are a little bit different. And so that remapping happens. And then when you call that inline function, Swift doesn't want to know how unions work. That's crazy. So what it does instead is it says, hey, Clang, you know how to do all this stuff. You know how to code generate all these things. And they both talk to the LLVM compiler that we were talking about last time. And so they actually talk to each other. They share the code. Clang does all that heavy lifting. And now it's both correct and it just works. Two things we like. And so these two things plug together really well, and now Swift can talk directly to C APIs. It's very nice. If you want to geek out about this, there's a whole talk. It's like a half hour, an hour long, talking about how all this stuff works at a lot lower level.
We will add that link to the lesson notes.
Yeah. So let's jump back to your example, because...
Okay. So one of the reasons I'm really interested in this description, Chris, is that it's kind of all about... one of the reasons I really wanted to work with you, apart from the fact that you're very amusing and entertaining, is that...
I'm easy to laugh at.
Yeah, absolutely. Is that this idea of what you did with Clang and Swift is like the kind of stuff that we're going to be seeing is what's happened with like how differentiation is getting added to Swift. And like this idea of like being able to pull on this entire compiler infrastructure, as you'll see, is actually going to allow us to do some similarly exciting and surprisingly amazing things in deep learning world.
And I'll say, this is all simple now, but actually getting these two massive systems to talk to each other was kind of heroic. And it was, getting Python integrated was comparatively easy because Python is super dynamic and C is not dynamic.
Yeah. And one thing I'll say about C libraries is each time I come across a C library, many of them have use these weird edge case things Chris described in surprising ways. And so I just wanted to point at a couple of pointers as to how you can deal with these weird edge cases. So when I started looking at kind of how do I create my own version of tf.data, I need to be able to read JPEG files, I need to be able to do image processing. I was interested in trying this library called VIPS. And VIPS is a really interesting C library for image processing. And so I started looking at at bringing in the C library. And so I started in exactly the way you've seen already. So let's do that. So you'll find, just like we have a Swift socks in the repo, there's also a Swift VIPS. And we'll start seeing some pretty familiar things. There's the same package.swift that you've seen before, but now it's got some extra lines we'll describe in a moment. There's the sources VIPS module map with the exact 3 lines of code that you've seen before. There's the sources VIPS some header, I called it a different name in this case, which has the 1 line of code which is connecting to the header. After you've done that, you can now import VIPS. Done. But it turns out that the VIPS documentation says that they actually added the ability to handle optional positional arguments.
In C.
In C. And so it turns out that you can do that in C, even though it's not officially part of C, by using something called varargs, which is basically in C. You can say the number of arguments that go here is kind of not defined ahead of time, and you can use something I've never heard of before called a sentinel, and basically you end up with stuff which looks like this. You end up with stuff which looks like this, where you basically say, I want to do a resize, and it has some arguments that are specified, like horizontal scale, and by default it makes the aspect ratio the same. But if you want to also change the aspect ratio and have a vertical scale, you literally write the string vscale, and that says, oh, the next argument is the vertical scale. And if you want to use some different interpolation kernel, you pass the word kernel, and you say there's some different interpolation kernel. Now this is tricky because for all the magic that Swift does do, it doesn't currently know how to deal with varargs and sentinels. It's an edge case of the C world that Swift hasn't handled yet.
I think this might be the last edge case.
Okay.
Jeremy has this amazing thing to find the breaking point of anything.
That's what I do.
Yes.
But no problem, right? The trick is to provide a header file where the things that Swift needs to call look like the things that they expect. So in this case, you can see I've actually written my own C library. Right? And so I added a C library by literally just putting into sources. I just created another directory, and in there I just dumped a C header file. Right? And here's the amazing thing. As soon as I do that, I can now add that C library, not pre-compiled, but actual C code I've just written, to my package.swift, and I can use that from Swift as well. Right? And so that means that I can wrap the VIPS weird varargs resize version with a non-varargs resize version where you always pass in vertical scale, for instance. And so now I can just go ahead and say VIPS load image. And then I can say VIPS get, and then I can pass that to Swift for TensorFlow in order to display it through matplotlib. Now, there's a really interesting thing here, which is when you're working with C, you have to deal with C memory management. So Swift has this fantastic reference counting system, which nearly always handles memory for you. Every C library handles memory management differently. So we're about to talk about OpenCV, which actually has its own reference counting system, believe it or not. But most of the time, the library will tell you, hey, this thing is going to allocate some memory, you have to free it later, right? And so here's a really cool trick. The VIPS get function says, hey, this memory, you're going to have to free it later. To free memory in C, you use the free function, because we can use C functions from Swift, we can use the free function. And I need to make sure that we call it when we're all done. And there's a super cool thing in Swift called defer. And defer says, run this piece of code before you finish doing whatever we're doing, which in this case would be before we exit from this function.
Yeah, so if you throw an exception, if you return early, like anything else, it will make sure to run that. And
And in this case, I probably didn't need defer because there isn't like exceptions being thrown or lots of different return places. But that's my habit, is that if I need to clean up memory, I just chuck it in a defer block. Or at least that's one of the two methods that I use. So that's that. So because I like finding the edges of things and then doing it anyway, the next thing I looked at, and this gives you a good sense of how much I hate tf.data, is I was trying to do anything I could to avoid tf.data. And so I thought, all right, let's try OpenCV. And for those of you that have been around FastAI for a while, you'll remember OpenCV is what we used in FastAI 0.7. And I loved it because it was like insanely fast. It's fast, reliable, high-quality code that covers a massive amount of computer vision. It's kind of like, it's what everybody uses if they can. And much to my sadness, we had to throw it out because it hates Python multiprocessing so much. It just kept creating weird race conditions and crashes and stalls on like literally the same code on the same operating system on two different AWS servers that were meant to be the same spec would give different results. So that was sad. So I was kind of hopeful maybe it'll work in Swift. So we gave it a go. And unfortunately, since I last looked at it, they threw away their C API entirely, and they're now C++ only. And Chris just told you we can't use C++ from Swift. But here's the good news. You can disguise it so Swift doesn't know that it's C++. And so the disguise needs to be a C header file that only contains C stuff, right? But what's in the C++ file behind the header file
can be anything.
Can be anything at all.
It can be Pascal. Clang knows Pascal calling conventions, and Swift can call them.
I didn't know that.
Pascal strings too.
So here's SwiftCV. And so SwiftCV has a very familiar looking package.swift that contains the stuff that we're used to, and it contains a very familiar looking OpenCV4 module map. Now OpenCV actually has more than one library, so we just have to list all the libraries. It has a very familiar looking, actually we don't even have sorry, that's right. So we didn't use the header file here because we're actually going to do it all from our own custom C++/C code. So I created a C OpenCV, and inside here you will find C++ code. And we actually largely stole this from the Go OpenCV wrapper, because Go also doesn't know how to talk to C++, but it does know how to talk to C. So that was a convenient way to kind of get started. And you can see that, for example, we can't call new because new is C++. But we can create a function called matNew that calls that, and then we can create a header that has matNew, and that's not C++, right? This is actually a plain C struct pointed to a struct, and so I can call that. And so even generics, C++ generics, we can handle this way. So OpenCV actually has a full-on multi-dimensional generic array, like NumPy, with like matrix multiplication, all the stuff in it. And the way its generic stuff works is that you can ask for a particular pixel and you say what data type is it using C++ generics. So we just create lots and lots of different versions, or all the different generic versions, which in the header file look like C. So once we've done all that, we can then say import SwiftCV and start using OpenCV stuff. So what does that look like? Well, now that we can use that, we can grab this, we can read an image, we can have a look at its size, we can get the underlying C pointer, and we can start doing, and we can start doing timing things and kind of see, is it actually looking like it's going to be hopeful in terms of performance, and so forth. I was very scared when I started seeing in Swift all these unsafe mutable pointers and whatnot.
They're designed to make you scared. It starts with unsafe.
Fair enough.
But this is C, right? And so C is inherently unsafe.
Yeah.
Swift's theory on that is that it does not prevent you from using it. It just makes it so you know that you're in that world.
But there's actually this great table I saw from Ray Wenderlich's website, and I've stolen it here. And basically what he pointed out is the names of all of these crazy pointer types actually have this very well-structured thing. They all start with unsafe, they all end with pointer, and in the middle there's this little mini language which is, can you change them or not? Are they typed or not? Do we know the count of the number of things in there or not? And what type of thing do they point to if they're typed? So once you kind of realize all of these names have that structure, suddenly things start seeming more reasonable again.
We have 2 questions.
All right, let's go with the 2 questions.
One is, are the C libraries dynamically linked or statically linked or compiled from source to be available in Swift?
Sure. By default, if you import them, they are statically linked. And so they'll link in with the normal linker flags, and if the library is a .a file, then it will get statically linked directly into your Swift code. If it's a .so file, then you'll dynamically link it, but it's still linked to your executable. All the linker stuff, so DL open, is a C API. And so if you want to, you can dynamically load C libraries, you can look up their symbols dynamically, you can do all that kind of stuff too.
Another question is, how much C do you have to know to do all these C-related imports?
Almost none, so like I don't really know any C at all. So I kind of like randomly press buttons until things start working or copy and paste other people's C code.
Yeah, the internet, Stack Overflow has a lot of helpful stuff.
Yeah, you need to know there's a thing called a header file, and that contains a list of the functions that you can call, and you need to know that you type hash include angle brackets header file, but you can just copy and paste the Swift socks library that I've already shown you, which has the 3 files already there. And so really you don't need to know any C, you just need to replace the word socks with the name of the library you're using. And then you need to know, you need to kind of work through the documentation that's in C, and that's the bit where it gets like, you know, I find the tab completion stuff is the best way to handle that, is like hit tab and you say let x equal, and then you call some function, and then you say x dot, and you see what's inside it, and things kind of start working.
And for all the hard time you give SOX as a, you know, not a web design firm, it has a pretty well-structured API. Mm-hmm. And so if you have a well-structured API like this, then using it is pretty straightforward. If you have something somebody hacked together, they didn't think about it, then it's probably going to be weird, and you may have to understand their API, and it may require you to understand a lot of C. But those are the APIs that you probably won't end up using, because if they haven't gotten a lot of love to their API, people aren't using it, usually.
My impression is that almost all of the examples of the future power of Swift seem to rely on not on the abstraction to higher levels, but on the diving into lower level details. As a data scientist, I try to avoid doing this. I only go low if I know there's a big performance gain to be had.
Let me say my perspective as a data sicentist, and then maybe we can hear your...
Well, and I was just going to inject, we're starting at the bottom. So we'll be getting much higher levels soon. But.
Yeah, but I mean, there's a reason that I'm wanting to teach this stuff, which is that I actually think as data scientists, this is our opportunity to be far more awesome. It's like being able to access, like, something I've noticed for the last 25 years is like everybody I know I mean, it didn't used to be called data science, but we used to call it like industrial mathematics or whatever, operated within the world that was accessible to them, right? So like at the moment, for example, there's a huge world of something called sparse convolutions that are, I know they're amazing. I've seen like competition winning solutions. They like get state-of-the-art results. There's like 2 people in the world doing it because it all requires custom CUDA kernels, you know. For years, for decades, almost nobody was doing differentiable programming because we had to calculate the derivatives by hand. So like, it's not just about, I want an extra, it's absolutely not about, I want an extra 5% of performance. It's about being able to do whatever's in your head. It's like, I used to be a management consultant, I'm afraid to say, and I didn't know how to program, and I knew Excel. And the day that I learned Visual Basic was like, oh, now I'm not limited to the things I can do in a spreadsheet, I can program. You know, and then when I learned Delphi, it was like, oh, now I'm not limited to the things that I can program in a spreadsheet, I can do things that are in my head. So that's where I want us all to get to.
Yep.
Okay, and some people are feeling overwhelmed with Swift, C, C++, Python,
Yeah, let's get out of this.
PyTorch, TensorFlow, Swift for TensorFlow. Do we need to become experts on all these different languages?
No.
No, we don't, but can I show why this is like super interesting? Because this is like, this like, so let me show you why I started going down this path, right? Which is that I was using tf.data. And I found that it took me 33 seconds to iterate through ImageNet. And I know that in Python, we have a notebook which Sylvain created to compare called timing. And the exact same thing takes 11.5 seconds. And like, this is not an insignificant difference. Waiting more than 3 times as long just to load the data is just not okay for me. So I thought, well, I bet OpenCV can do it fast. So I created this little OpenCV thing. And then I created a little test program. So this is the entirety of my test program, right, which is something that downloads ImageNet and reads and resizes images and does it with 4 threads. And so if you go Swift run, Swift run, okay, so when I run this, check this out, 7.2 seconds. Right? And so this was like half a day's work. And half a day's work, I have something that can give me an image processing pipeline that's even faster than PyTorch. And so it's not just like, oh, we can now do things a bit faster, but it's now like anytime I get stuck that I can't do something, it's not in the library I want, or it's so slow as to be unusable, you know, this whole world's open. So I'd say like we don't really touch this stuff until you get to a point where you have no choice but to, and at that point, you're just really glad it's there.
Well, and to me, I think it's also, the capability is important even if you don't do it. So keep in mind, this is all code that's in a workbook. So you can get code in the workbook from anywhere. And now you can share that workbook, and you don't have to share this like tangled web of dependencies that have to go with the workbook. And so the fact that you can do this in Swift doesn't mean that you yourself have to write the code, but it means you can build on code that other people wrote. And if you haven't seen Swift at all, if this is your first exposure to it, this is definitely not the place you start. Like the data APIs that we're about to look at would be a much more reasonable place to start. You've had a month or 2 months worth of hacking with Swift time, and that's Jeremy months, so that's like a year for normal people. So this being like super powerful and the ability to do this is I think really great, and I agree with you.
Yeah, and I am totally not a C programmer at all, and honestly it's been more like 2 weeks, because before that I was actually teaching a Python course, believe it or not, but Sylvain's been doing this for a month.
Yeah, so I mean, so this is it's all there, and I would definitely recommend ignoring all of this stuff, and we're about to start zooming up the levels of the stack. But the fact that it's there, I think, is reassuring, because one of the challenges that we have with Python is that you get this ceiling. And if you get up to the ceiling, then there's no going further without this crazy amount of complexity. And whether that be concurrency, or whether that be C APIs, or whether that be other things, that prevents the next steps and the next levels of innovation and the industry moving forward.
And this is meant to be giving you enough to go on with until a year's time course as well. Yeah. So like it's hopefully this is something where you can pick and choose which bits you want to dig into, and whichever bit you pick to dig into, we're showing you all the depth that you can dig into over the next 12 months.